we've been working with polynomial functions, all of those like more obvious ones that we work with on our cheat sheet with polynomials. So when we talked about x squared, x cubed, so when we did these and this guy and even to the fourth power, all of them that are smooth and curvy like this are polynomial functions. And we talked about end behavior, which we will talk about more today. And this is about where we left off last year with our polynomial function. We did that big project, which I don't have anymore. So maybe we'll take a look at what my Algebra 2 class did this year as a reminder. So polynomial functions have rules. So the rule is that the exponent of x, right, of the variable is a positive integer, which means it's like a positive whole number, right? So it can't be a half or a third, and it can't be a negative number like -1. And when that happens, polynomial functions, when we write them out, so for example, let's see one that I could write out. Let's see, because I want to show you a graph that's pretty. The book has this example. They say if f of x equals x to the fourth minus 3x cubed minus 5x squared plus 8, and they've even graphed it, and I'm going to show you what the graph looks like, sort of. It's going to be a guesstimate, okay, but we can look at it once we know the definition of polynomial and say, okay, this is a polynomial graph because it has all the exponents are positive and they're whole numbers. None of them, the x's are in the bottom, there's no fractions. And that means that the graph will look like, that's kind of part of the definition, it will be, I guess I'll just add it here, the graph is smooth and curvy. And that doesn't seem like very much of a definition, but it means it's not something like absolute value. It's not pointy. It never like comes to a point and then changes. If it has any sort of minimum, and mine kind of looks a little pointy there, but it comes up to it gradually and then it goes back up. So it's never pointy. So that's just good to know. If you go further into mathematics, we look for things like slopes of the various points on this graph. So some of this graph has negative slope because it's going down all the way to here. And then it starts to go up, but the slope is not like a line. It's not the same everywhere. So smooth and curvy means I could find the slope everywhere. So that's important to the definition of a polynomial function. So along with this, we want to define things about it. So what do we remember from this x to the fourth? What do we remember? Why does the graph look like this? Is there anything that you remember from last year that would help us? Yep.
No, I don't know.
So we can make a guess about some things for the curve based on the biggest degree. So x to the fourth, as we move further from the origin, x to the fourth defines what happens in our graph. So we call, I'm going to use this as our example, f of x has degree 4. So degree is one of our vocabulary words from last year. Degree means the highest exponent. And because it's a degree 4, we talked about last year that even exponents like 4 mean that it will have the same behavior. So on the video you can't see me, I'm holding both of my hands up because Degree 4 means it's both going to end up on the ends. Some things might happen in the middle behavior, but the end behavior is based on what degree it is. So f of x has degree 4, so even end behavior, which means at x goes to infinity, and as x goes backwards to negative infinity, so this is x goes to infinity, and this is x goes to negative infinity. That does not show up, so let me write that better. On this side, x goes to negative infinity. We're actually going this way, but I write it in words the other way. We can describe the y values. So for this example, both the y's are going up. So y is also going up. Y is going up on both ends. So we're looking at it in terms of horizontal. What's happening as we go this way? The graph goes up, that's infinity. As we go this way, the graph is still going up, it's going to infinity. And that's determined by the highest degree. So we're going to make a chart about that. We did it last year, but we're going to do it again in a minute. But while I'm looking at this, this also has a leading coefficient. What is the leading coefficient? That barely fed in there. What's the leading coefficient for this graph? For this function f of x? Being the leader implies it's in the front. What's the very first quantity we have? So x to the fourth, that's the degree. How many x to the fourth do we have? So it's 1. That 1 is our leading coefficient. Remember, we talked about if this number was negative, the whole thing would flip to down. Do you remember that from last year? So that's what I'm talking about, is remembering some of this polynomial definition stuff, because we can get a lot based on what the degree is and what the leading coefficient is and things like that. So all of this talks about end behavior. This is end behavior. We're talking about x goes to positive or negative infinity. When we talk about middle behavior, we would write how f of x is factored. In this example, I don't actually have how this factored. It must factor as 1, 2, 3, 4. It's like 4.5. It's something like, I don't know how it factors. I don't know. We'll have to do another one that I can actually factor in a minute. But when it's factored, we get the zeros, and the zeros equal x-intercepts, and those are points like this. So I just kind of pulled this graph from the book. I don't know exactly what those points are, and I should have 4 of them, and I only showed 2. So I've got some imaginary roots too, so I don't see them all. But middle behavior is around the origin, and it is described on our graph by where it crosses the x-axis, or it could be the y-intercepts. We could plug in 0 and find the y-intercept. That would be easy to do here, because if we plug in 0, we'd have 0, 0, 0, 8. So like that is really easy to find. This value must be 8. That's the only thing I do know, okay? So we'll go through some actual examples, but I wanted to discuss some of the vocabulary that we did last year and make it feel fresh for this year for you. So end behavior and middle behavior, function notation. While I've got all of these things up here, polynomials also, so these are like bullet points. This is another bullet point for polynomials, but I'll write polynomials here. Polynomials have all real numbers for domain. And that's because polynomials, since their definition at the top, since the definition is that we have positive integer exponents, there's never an x in the bottom, and there's never a 1/2 for an exponent, so there's no square roots. So those are the only two things that would limit our domain, and we don't have any of those here. So we could always write for polynomials, the domain is all real numbers. Oops, you can't see that on the video. There you go, all real numbers. All right, let's take a look at what we might want to do in order to work some problems for this section. First, we have the idea of substitution. So, our first couple of problems say verify the given values of x, solve the polynomial equation. So what they mean is, if you had, I'm going to find a different example. Okay, if we had f of x equals 6x squared minus x cubed. I'm wrong, that's not how they wrote it. They didn't write f of x here. So cross that out or erase it. They have it equal to another polynomial, 12 plus 5x. So they have written it as this polynomial equals this polynomial. That indicates that they intersect somewhere, but right now in our directions, we just want to verify that 4 works. So really all you have to do is substitute it in. So you're given this, you're given a value, you need to see if it works and show the math for that. So you're going to write 6 and then 4 squared minus 4 cubed, 12 plus 5 times 4. So they want you to work that out. After you substitute in, let's see, what is that? 6 times 16 minus 64 equals 12 plus 20, 32. So 36, 96. 96 minus 64 equals 32. 6 minus 4 is 2. 9 minus 6 is 32. That does verify. So you would just show that you understand that that's the place at x equals 4 is where this graph would cross this graph. And we will actually graph some on our calculator to get good at that too. And you just need to plug it in. Okay, so we're going to do that. Just a couple problems. That's pretty straightforward. Then we have where I told you we were going to review all of the different degrees. And so we're going to make a chart. It's going to have 4 sections like so. Try to squeeze all this in there. So there are 4 possibilities of graphs. You can have even exponents, like the degree. The highest one, the actual degree is a better word here than exponent. My pen's dead, so that's gone. For example, y equals x squared, or y equals 4x to the 4th, or y equals 3x to the 6th plus x cubed. Those are 3 random examples. They're all going to graph differently, but they all do have an even degree because this is the highest exponent 2, and then 4, and then 6, they all have an even degree. So not just an even exponent, because this one has an odd exponent, but an even degree. And they also have, in this case, positive leading coefficient. So what happens with the end behavior here? Do my ends go the same or opposite or both up, both down? What happens with y equals x squared? You remember, what does x squared look like? I know, but this was a quadratic, like we've done that before. What does just a regular x squared look like? We call those parabolas, right? Do they have the same behavior or do they go opposite?
No,
they have the same behavior. So all of these even ones are going to have up in behavior. Okay, they might have some other middle behavior. They might, if it was just the parabola, it would look like this. It might look like this. But the end behavior is going to be up. If it's even, but it has, so if we said negative x squared, or y equals negative 2x to the fourth, or anything that's even up here, but negative leading coefficient, that takes the same graph and flips it over. So then we would have whatever happens in the middle, but both ends go in the same direction. We might have some other things happening in the middle, but I know for sure that both ends are going to go down. And we write that like this, where we say, as x goes to infinity on this side, the y goes up, so infinity. And on this side, we could say, as x goes to negative infinity, y goes to infinity. So that both the y's go to the same place. Both the y's go to the same place here. It's just that these y's go to negative infinity. And this is how we write it in math. Okay? But this is what I'm talking about as far as end behavior. Now, odd degrees are different. So this was my even section. Even. Now I'm going to look at odd degree. So that's the highest exponent. And odd degrees for polynomials start with a line. Okay? You remember y equals x looks like this. Goes to the origin, but it goes like this. One end goes up and one end goes down. Well, the same thing happens with x cubed, except it has sort of a wiggle in it because it's got a higher power. And then x to the fifth, oopsies, x to the fifth looks kind of like x to the third, but it's actually like flatter here. And if we had other things added to it, like x to the fourth and x to the third, like y equals x to the fifth plus 3x to the second power plus 7, like this equation, I don't know exactly what it looks like, but I know it would go up on this side, and then it would go something like that. It has more wiggles in it with these other things added. But what's different between this one up here and this one right here is that on my odd degree, as x goes to infinity and y goes to infinity, now when x goes to negative infinity, y does something different. It didn't do that. Up here, y did the same thing. If it's an odd degree, the y's do something different. One's positive and one's negative. So this represents all positive leading coefficients. And on the other side, if we still have odd powers, if we just throw a negative in there, negative x, then our slope is negative. For the line, it goes the other way. See, it switched. So on the left, it goes up, and on the right, it goes down. So we have Saturday Night Fever that's switched. So this is a negative leading coefficient. And it's in behavior, switches sides. Okay? That all should feel familiar from last year. We talked about it a lot. I did a lot of using my hands to represent Saturday Night Fever and stuff. So I'm calling this Saturday Night Fever. I guess I would call this the backwards one because we switched it, or the switched ones, because we had a negative leading coefficient. Maybe this is y equals negative x cubed plus 2, something like that. It's been moved. So odd and even. Okay. New page. That was in behavior. Let's talk about middle behavior. We spend a lot of time in this class factoring, and this is where it becomes useful. The factored version of the polynomial tells us about middle behavior. It tells us the zeros. And zeros equal the x-intercept. They equal what we call the solutions. If we try to solve for x, we get that. Zeros, x-intercept, solutions, anything else? No. But we have to factor it to be able to see what those are unless we're using a calculator. So let's do a couple of examples and see if we can see what I mean. Let's look at one already factored. So if I say x plus 2 times 2x plus 5 times x minus 7, I can tell you a whole bunch of things about this. I could multiply it all the way out, but I don't want to, so I'm not going to. But if I did, if I multiplied these two together, what would I get? Just the first two values. 2x squared, right? Yes? 2x squared. If I multiplied 2x squared by this x, then I would get 3x. Oh, I wouldn't get 3x. I would get a 3 somewhere, but not there. I would get 2x cubed. So if I said 2x squared times another x, I get 2x cubed. Tell me about in behavior for that. We just did that. Is it odd or even? Even though there's a 2 in there, is this function odd or even? Is it an odd degree or an even degree? So degree means exponent. Even or odd? Yep. The exponent. So 2 is the leading coefficient. And it's positive. That's important. But then 3 is our exponent. So it's a third degree, which means it's odd, which means it's going to have something like this in behavior. So I need you to be able to think through that far. And if you need to, you could multiply this all out. It would be fine to do that. The reason I wouldn't want to is because now that it's factored, for me to be able to find zeros, if I go and set it equal to 0, the factored version with the 0 product rule, we need the 0 product rule. That's my favorite because it says, hey, if you multiply a number by 0, you still get 0. Let's say 0 times 4, I get 0. 0 times 7, 0. 0 times 10, 0. The 0 product rule says you multiply anything, that's what product means. Anything by 0, you get 0. So if you set a polynomial equal to 0 in the factored form, that lets you make tiny equations to solve. That doesn't say tiny. Tiny equations to solve. Meaning I can say x plus 2 equals 0 and 2x plus 5 equals 0 and x minus 7 equals 0, and that will tell me about middle behavior. So solve these for me. Isabel, what do you get with the first one? -2. How about the second one? We need extra stuff with that one. -5. 2x equals -5 divided by 2. X equals -5 halves. Or what's that? Like -2.5. Javier, but this one. X minus 7 equals 0. What's X? 7. And so now that we know two things, we know kind of what it looks like. This tells us where it looks like that. Let's graph it. It's not a perfect graph, but it's a sketch. So we can put a 0, meaning this is a point, -2, 0. And this is a point, -2.5, 0. And this is a point, 7, 0. They're all zeros. Here I go, 1, 2, 3, 4, 5, 6, 7, 0. -2.5, 1, 2, 3, 2.5. Should have chosen some further apart. That was bad on my part. I also have -2 as a 0 right here next to it. Because this was a third degree, and I marked this third, I have 3 zeros usually. And I have this in behavior, which says that on the right, it goes up. So on the right point, I go up. What happens at the left point? Goes down. So I go to the left point and it goes down. And what happens in the middle is it goes through the points like this. I did something. I just made up my own there. I was just making stuff pretty. Ignore that. That didn't happen. Just kidding. It did happen. Okay, so it goes through this. It comes back through 2 and goes down again. I have this little tiny loop right there. I don't know what I was drawing before. I was just drawing something willy-nilly. I have to go through this 0 and then these other 2 zeros. That's the only zeros I have. See, they're right here. 1, 2, 3. This is not a perfect sketch. This could actually go like lower. But the general shape of it we can get from in behavior and zeros. So definition-wise, I need to know what zeros are. I need to know what factored form looks like. And then some of the problems that you have to factor, they're not that difficult. You'll be able to factor them. But you definitely have to set it equal to 0. It doesn't work without the 0 product rule. So what you have for homework for me is to be able to tell about the leading coefficient, and degree, to tell about the end behavior as we talk about infinity, and it tells you that in the stuff, to be able to plug in and tell if it's a 0 or not. And then we'll build on that tomorrow. So your homework's going to be on page 322, and I'll pick up those problems and post them on Google Classroom, and that's the end of this video.